x momentum equation that comes from Navier-Stokes, we end up getting this equation right here, right, where I've non-dimensionalized the differential terms right here. So all these stars mean they're non-dimensional differential quantities. I'm left with my parameters on the outside, right? And this is for the x momentum equation. Extra credit, I've told you to do this for the y momentum equation and come to a famous conclusion about the pressure term. Actually, conclude yourself, but do this process and then look at the size of these terms to try to come up with a conclusion about something. It's fun. So, as always, right, sort of all the dimensionality now is kept up in these parameter terms that are on the outside of these non-dimensional differential terms, right? Keep in mind, this is ND, right? Non-dimensional, right? So all the dimensionality is kept up in these exterior terms. So that's why, right, it's very easy now to non-dimensionalize the entire equation because you just divide one side by the other. And it makes physical sense as to one thing we're going to do. We're going to divide the whole term by this. So divide this entire equation by multiply through this whole thing by this. Why are we doing that? Right? Because we're trying to look at the balance of the inertial side of Navier-Stokes to the viscous side and try to see is there a balance between the two, which one matters more. And we also understand now when we take that balance of inertial to viscous, we're getting Reynolds numbers. So you'll see it play out again. So multiply through this whole equation. That goes away. This goes away. I'll just rewrite it. Okay, after you do that, and now we'll have another sort of tricky thing. So after you've done that, all that's left is this parameter, right, multiplying the curvature of the velocity in the x, and this multiplying the curvature of the velocity in the y. Remember, we also could kind of understand what should be happening right now. Here's y, here's u, right? So we see there is curvature that's happening if I go from 0 to the infinity, so we should know that this term matters more. But we can get there. So, right, here's where we didn't really know what this term is. Right, we didn't really know exactly what this delta was. But before, do you remember that I did show you before with a little balance? I knew that this over L scales like 1 over a Reynolds number with respect to L. Remember, like last time we showed that, so you can think of that as L, the Reynolds number. And that's important because right here you see that this is 1 over a Reynolds number with respect to the L coordinate. And this is 1 over a Reynolds number with respect to the boundary layer distance. So I have two competing Reynolds numbers that I'd have to measure, or I'd have to calculate to see which one of these matters more. But this relationship that the boundary layer is proportional to the inverse of the Reynolds number with respect to the L eliminates this one. Right? So just plugging in this relationship into here, you'll get, very important, okay? This half power is what's important. And that comes from this argument that the delta is proportional to the inverse of the Reynolds number. But the idea that now this is the half power. That becomes important because we say in boundary layer that the Reynolds number is fairly large, not huge, right? Certainly not small, because we saw that there was a different drag law that happened if it was small. It has Stokes, right? Just the drag force, the drag force follows different laws. But if it's getting kind of big, we see that this term matters far more, right? And that's critical for boundary layer analysis, right? This half power, right? One example is like if, say it's right, say you have Reynolds number this, it's still pretty, right? It's still a fairly large number comparing, right? This number way smaller than this number, right? It's the square root 36, so 1 divided by, right, 1 divided by 1300 compared to 1 divided by 36. This is a smallish number, but like nowhere near as small as the full power, right? We get issues if Reynolds number is much, much less than 1, but that's not what we consider with boundary layer. We only talk about when the Reynolds number is like greater than 1. So sometimes you say much, much greater. So that's critical. So really consider about, right? So that's sort of the important part is now I just have one Reynolds number I need to care about. Right? For this situation, I have a characteristic length of my plate or foil or whatever that's in the external body, right? And the sort of the Reynolds number that will govern this, that will tell me everything, is sort of naturally what we had. I got rid of the delta and then can make the assumptions that you have what matters.